acceleration. It starts from rest and then starts to accelerate. Right? So great, that's looking good. And now if I isolate a sub x, what do I find? Well, let's see. I can divide everybody by r. In fact, I can divide everybody by m and r, because there's an m and r here, there's an m and r here. If I do that, then I get an mr squared down here, which has the same units as this, so that feels good. Oh no, except I've got the mass left over. Great. So what do I get? I get g times sine gamma divided by, is this, what did I say I was going to do? I've got a 1 there plus an I center of mass, very important, right, because we did this all with the pivot point center of mass, divided by mr squared. Does everyone agree with that? I don't think I'm making mistakes, so I just did it on the fly, so it's possible there's a mistake there. Well, let's check our units. This thing's an acceleration. Oh, also, what was our question? Our question is acceleration constant or not? Well, let's see. Do any of these things depend on time? G doesn't. It's always 10 meters per second squared. Gamma doesn't. It's just the angle of the ramp. As long as you have a flat ramp, right? This is some fixed constant. It doesn't depend. So there you have it. It's constant acceleration. So that answers the main thing we wanted to know. Let's just check real quick. Units make sense. This is an acceleration. This is an acceleration. Same units, right? 10 meters per second squared. Sine of gamma is just a number. No units, right? This is a number. Number 1. No units. This thing has the same units as this. Mass times length squared. So no units. So good. The units are right. This is a miraculous discovery here, actually. What else do we need? Let's look at the limits real quick. So does this make sense? Suppose the wheel had no moments of inertia. All the mass is concentrated at the center of the wheel. So that means that this would be 0. If this is 0, then this whole ratio is 0. 1 plus 0 is 1, so you get rid of the whole denominator, and you get a sub x equals g sine of the angle of the ramp. Well, we know that's true. We've solved that a few times now. The frictionless ramp case, that's it. Acceleration down the ramp is g sine gamma, where gamma is the angle of the ramp, right? So this formula looks good. It says that the acceleration goes down when I goes up. The bigger the moment of inertia, the less the acceleration. And you can imagine that. Suppose I have a big massive wheel with big moment of inertia on there, and then we let it start roll. It would slowly start to roll, because it actually takes a lot of torque acting for a long time to get that wheel to start, right? Start moving. So good, we solved it. And the way we solved it was by combining, like we still had to use plain old Newton's second law, in addition to this new Newton's second law for rotations. And we had to relate acceleration, the linear acceleration of the center of mass, to the angular acceleration. This is the general sort of form these problems take. You wind up having to relate those things. So there's another way we could solve this problem. Actually, a couple of ways we could have solved it, but there's another way we could solve it with a different choice of pivot point. So I told you there's 2 legal choices for pivot points. One's the center of mass. What's the other one? Let's go back to our ramp over here. If I've got a wheel going down this ramp, is there a stationary point at any moment in time on the wheel? Yeah. Where is it? It's right where the wheel meets the ramp. So we could have done this whole problem with that pivot point. And students freak out when that, because it's weird to think about the torques. When you calculate the torque, we'll get more freak out. But when you calculate the torques, it's surprising. So let's think about what the torques would look like. If we solved it that way, then let's go to this picture right here. So let's solve it that way. We do our net torque. We get a torque due to, well, what is the torque going to be due to the normal force? Our pivot point, we're set for this problem. Now we're going to do it right here. Here's our pivot point, right where the wheel meets the ramp. So if the normal force acts at that point, torque's equal to 0 because the radial arm is 0. Same thing for the frictional force. So if we chose that point as our pivot point, which is legal, it's a little weird, but you're allowed to do it, that means that there's no torque from either of these. But there is a torque from gravity. The distance from where the pivot point is to where gravity acts is capital R. But notice that there's a non-right angle. It's not a right angle anymore between. So for one thing, is it a positive or a negative torque? Gravity's torque using this as your pivot point. Would you call that a positive or negative torque due to gravity? The way to think about it is you put a nail right through this part of the object, have gravity act this way on this point right here, and that's the only force in the problem. Which way will the wheel want to spin? This way or that way? Positive or negative? Positive. So it's a positive torque. Somebody had their hand up. No? Oh, that's me their hand up. All right. Good. Positive torque. So if we did the problem that way, we have only one torque in the problem for Newton's second law of rotation. And notice, this part would be the same. Everything up here, Newton's second law, linear stuff, all the same. Only when we get down here it changes, because we changed our pivot point. So then we get an equation that says what? Let's see. I'll say pivot point equals contact point. Contact point, right? Just so where the wheel meets the road. In that case, what you get, well, it's Newton's second law for rotations. We find the net torque. What is it? There's only one that contributes. It's gravity. It's positive force of gravity, which is mg, right? Times the total length of the radius from the middle of this capital R, so where the force acts. And now we need is it a sine or a cosine? Well, it's this distance. So I want, here's force of gravity. If I want to know what the orthogonal component, this is it right here, it's going to be sine, right, of gamma. So it's going to be mg sine theta times r. Or if you like, r sine theta times mg, either way. I just happen to draw it, or not theta, gamma. Equals IAX over, that's right, IAX over r. So you might say, wait a minute, I just used this rule about substituting in for alpha AX over r. Is that still valid? I changed my pivot point. Turns out it's still valid. The relationship between the angular acceleration of the object and the linear acceleration of the center of mass are the same no matter what pivot point you choose. Okay? But you might look at this and say, wait, this is a different equation. You get a different answer now. But there's something that's changed that I haven't changed yet in the equation. What is that? What is different with my new pivot point that I haven't explicitly mentioned yet? So what's in this equation? There's the mass of the object, there's acceleration due to gravity, the radius of the object, gamma, the moment of inertia. What are those things changes when you change your pivot point? Oh, no, I'm not quite clear. Moment of inertia changes. Is it bigger or smaller now than it was before? So before we did center of mass. If we go from the center of mass to some other pivot point that's far from the center of mass, did our moment of inertia go up or down? Up. By how much? Can we calculate it some way? What theorem do we use? Parallel axis theorem. Parallel axis theorem, right, says that the moment of inertia, the new one we need for here, right, that equals the center of mass moment of inertia plus, well, what's it going to be? It's the mass of the object, that's m, times the distance we move the axis squared. That distance is what? Capital R. So we get capital R squared. So if we take this formula, plug that in for here, now we get an equation that's the same. So we had to make 2 changes. We had to change our moment of inertia, and we have a simple formula for doing that, the parallax constant, and we had to change all of our torques, right, in our Newton's second law of rotations, and then when the death clears, you get the same answer. So just be consistent whichever way you do it. Don't change it up halfway through. Suppose we were asked in this problem, I guess, wow, I did a lot of calculation. We're running low. So what I'm going to do is, yeah. So the answer to that, you're saying, when would you do one or the other for where you put your pivot point? The answer is, in this problem, I would do either one with equal likelihood. The reason I think it's a little easier for most students to put it at the center is it's easier to think about torque about the center of the wheel. A lot of students will get their signs wrong or get confused and get the pivot point down here. That's the case where the wheel is, you're thinking about the wheel as rotating around an edge of the wheel. It's perfectly valid. It's the right answer. In fact, there's cases where it's way easier to do that. In fact, so we didn't get as far. I'm not going to solve this guy today, probably, which I wanted to do. But yeah, 15 minutes is a little bit tight to do that one. But I want to do one more thing. I'll do one more thing with the ramp, and we'll do some demos with the thing momentum. But I'll show you an example. I'll show you an example in next lecture where we solve for this guy. We figure out which way it's going to go, and I pull the rope. Some of you saw that last week. Not all of you were in lecture last week, so it's because of the midterm. But I'll solve that problem, and we'll see which way it goes. Actually, well, should I do that now? Maybe let's do this right now, and I'll answer your question. And that's actually kind of fun. So how many of you were not here last week? Didn't see this. So I'll do this for your benefit. Those of you who were, don't vote. So if I have no friction and I pull up, is it going to? And there's no friction on the table, then it would just spin, right? But if there is friction, I've got my little friction pad, right? If I pull straight up, which way is it going to go? Your right or your left? For those of you who haven't seen it before. Correct. And then if I do this, right? So now I've got so it's coming over the top. Over the top. That's this class, right? Over the top. If I pull on, it's going to come to your left or your right. I said coming. I was like, okay. So now the other way. This is the hard way, right? So if I do it this way, which way is it going to go? To your right or your left? So those of you who didn't vote before, who thinks it's going to go to your right? Who thinks your left? There it is. And you've seen it before, and you're still like, when's midterm 2 again? Yeah, it's coming up, right? So how do we calculate that? How do we think about it? And this is a problem the teacher would calculate if you use the bottom point. So let's work it out. Here, I'll work it out right here. So we've got our wheel with 2 radii. It's a spool. It's got 2 radii, right? It's got an inner radius, we'll call it little r, got a big radius, we'll call it big R. And the question is, and what's our question? Which way does it go? How do we quantify that question? Left or right? Well, when we quantify it, we say, well, is a sub x greater than or less than 0? That's the question. Where this is the x direction. This is a horizontal plane here. Let's make this the x direction, make this the y direction. And I'm going to do it the other way around the way I had it. So let's say I pull this way. And there's tension T on the rope, okay? Right? So let's make our free body diagram. Well, there's how many forces? There's tension. Which way does tension point? To the right. Which way does gravity point? Straight down. Which way does normal force? Straight up. Right? Which way does friction point here? Again, it's static friction. It's rolling without slipping. Points to the left. So friction is static. So now we'll do our free body diagram extended. Right? Alpha or extended or whatever. So now let's draw our circle. Let's draw our inner circle. Here's the point of contact with the ground. The friction acts right here at the bottom. Points to the left. Right? Or correct? Right? Force of friction. Normal force, right at the bottom, points straight up. Right? Force of gravity effectively acts at the center of mass. So we have a downward force right here of mg. What else is there? Oh yeah, tension. Where does tension act? It acts right here. Does everyone see that? When I'm pulling on this, where's the rope actually exerting a force on this object? It's right here at the bottom of the spool, of the inner radius. Okay? 4 forces, 4 torques. So now we do Newton's second law for the x direction. What is Newton's second law in the x? Oh yeah, x is horizontal. Did I write that? Yes, I did. X is in the horizontal direction. Well, there's only 2 forces that play a role, right? Force of friction. So I get negative force of friction, positive tension equals max. And what am I being asked for? I'm trying to find out whether ax is positive or negative. That's the question. So good. I've got an equation with the thing I want. Now we can do Newton's second law in y direction, but it's not going to give us any useful because it's just going to tell us the normal force equals gravity. So now what we need to do is look at Newton's second law for rotation, right? Okay, so we have our net torque. What is our net torque? We have 4 possible torques. So there's torque due to friction, torque due to normal force, torque due to gravity, and torque due to what's left. Tension, thank you, equals I alpha. Let's do center of mass. Okay, so that tells me my pivot point I'm using. It says that this is my pivot point. If we do that, what do we find? We find the force. Let's see. So the normal force. What does the torque do to the normal force? It's pointing right at center of mass, right? So what is it? 0. What's the torque do to gravity? 0. Only 2. But now we've got 2 non-zero torques. See that? But they're easy to calculate because the angles are 90 degrees in both cases. In one case, there's 2 different r's, 2 different radii in the problem. So be really careful about which one you mean. I chose my notation so it's easy to remember. Small r is the inner one, and big r is the outer one. So for the force of friction, is it the little r or the big R? Big R. Is it positive or negative torque? So for friction, right. It's positive torque. And you might say, wait, you didn't find your positive direction for rotation. I'm using the same notation, same convention here, I mean. Positive is clockwise. So force of friction is pointing that way at the bottom of the wheel. It's trying to spin the wheel this way. You see that? Because the force of friction is pointing that way at the bottom of the wheel. If that were the only force in the problem, forget the rope when you figure out the sign of the torque due to friction. Just forget about the rope right now. It's going like this. It's trying to rotate the wheel this way. So that's a positive torque. So I say positive big R times force of friction. Now what about the force due to tension? What kind of torque do I get? A positive or negative torque due to tension? Remember, our pivot point is the center of the wheel. So you put a nail through the center of the wheel and just pull the rope. Which way would the wheel spin? Counterclockwise. That's why most of you voted the other way. Most of you being all of you, right? There's only one guy. Where is he? He voted the way. He got it right. But I remember people very seldom. I'd say people very seldom get that right. I did it right. And I still get to teach class. Anyway, so I get to. I get anyway. All right, so minus. All right, little r. I love teaching this class. To tell you the truth. A lot of fun. I wish I had these spools at home. I do not. This is right. Come in. What do I need? I need a normal force. No, tension. Does everyone agree with the sign and the symbols? So it's opposite direction. Little r tension. What does this equal? It equals I center of mass times alpha. But we can rewrite alpha because we have a relationship. Alpha is a sub x over. Is it big R or little r? Big R, because that's what's rolling on the ground. Big R distance from the ground, right? And is this positive or negative? So if alpha is positive, given my direction, is the wheel going to move to the right or the left? The right, and that's the direction that's positive x, so it's positive. Same as for the last problem, except last one the angle is downhill. Great, so now we've got our formula. You've already pumped in the extra piece of information how to relate alpha and a. Yes? Well, the answer doesn't make sense if you get the sign wrong for the torque. It's just like anything else. Suppose you put something down, if you get a sign error halfway through the calculation, when you get an answer, check to make sure it makes sense. Like on this problem, we actually check to make sure we got a positive answer, agreed with, for acceleration. Anyway, we check a bunch of things to make sure it makes sense. Those are limiting cases. If you get the sign wrong, you'll get crazy stuff at the end. If you have a wherewithal, you're not too punchy after doing the problem, to just look at it and say, oh yeah, that doesn't make sense. You can go back and find your error. I don't have an extra way to check per se, but I have a procedure I go through to see put a nail through the pivot point as you define it, and then exert only that force and see which way it rotates. So let's see what we got. Let's combine these equations. The top equation says, it allows us to solve for the thing we don't know. it says force of friction is equal to T minus ma. So I can say this is T minus ma, right, minus RT equals I center of mass AX over R. Does that look right? I think that's correct. I want to know what A sub x is. So now I isolate A sub x. Oh yeah, so what do I get? I get it equals R over I. That's correct. Times. Oh gosh. Oh, I see what I did wrong. I'm trying to do too much at once as usual. I need to combine my A sub x's first here. So let's do this. We have A sub x times what? I CM over R. And now let's add to it M times capital R. Right? That equals T times R minus little r. Does everyone agree with that? That says that A sub x equals T times R minus little r all over. Oh, let's just multiply by R. Jeez. Put an R in there. Put an R down here. And I get an I center of mass plus mr squared. Does everyone agree with that? Let's see if that's the right units. I've got acceleration meter per second squared. So then this thing is going to be T as a force, right? And this thing, oh yeah, so these guys all have kilogram meter squared. This is meter squared. Good. So this is force over meters. Good. Force over meters equals acceleration. My units are correct. Is this positive or negative? Well, if big R is bigger than little r, it's positive. And that's correct. When I pulled on the rope, if I pulled on it from this side, it would come toward me. That's the positive x direction. I got it right. If this were the other way around, it'd go the other way. And we can check all these other limits, and they all work out. It's not a complicated expression. So we just solved that by doing the center mass of our pivot point. Suppose we had done it with the pivot point at the bottom. How many non-zero torques would we have? Well, the normal force is acting at the pivot point. There's no torque. Force of gravity points right at the pivot point. There's no torque. In fact, the force of friction acts right at the pivot point. See that? If we use the pivot point at the bottom of the wheel, right, then there's only one non-zero torque. It's the one due to the rope. And so when we think about this problem, the reason you can see intuitively why it should come towards you is that if you choose the bottom of the wheel as your pivot point. So here, the bottom of the wheel is the pivot point, right? See that? It's rotating, and then that's the stationary point. That little point is not moving. If I pull this way, the only torque in the problem that survives about this pivot point is the torque due to the rope. Which way does that go? Clockwise or counterclockwise? Is this counterclockwise or clockwise? Well, I'm exerting a force this way on a point that's up here. It's above the ground. So is that a positive or a negative torque given my positive torque convention? It's a negative torque. And if it's this, and if I do it this way, it'd be a positive torque. If this is the way I set the problem up on the board, I pull that this way. In this case, yeah, it's positive torque this way, right? Because I'm exerting a force to the right at a point that's above the pivot point. And that's really weird. Like you usually think of spools as, like the reason our intuition's wrong when we first see this problem is that we just can't help but think of this as the pivot point. But in fact, if you think of it as down here, then there's only one non-zero torque. It's the one to the rope, and it goes the direction. So that's a quick way to do it. So there's a case where it's quicker, but you have to be pretty facile with the stuff to get the signs right. All right, well, okay, so we're running at the last minute. So in the last minute, what I'll say is that, so is anyone interested in doing this? Is sitting on this thing and spinning around? I don't know. If you have time, maybe I'll bring this out. Maybe I'll bring this out next time. I like this demo. I'll bring it back. The demo guy, Roberto's going to be angry. They can bring it back out. But I'll bring this back out. And so there's one more thing I was going to mention. Oh yeah, and kinetic energy. So next lecture we'll do kinetic energy for rotations, and we'll do a really brief thing about this, and then it's on statics. We'll see you next time.